Divya, can you hear me?
Hello.
Divya,
Yes, sir,
can
you
hear
are
me?
audible. Yes,
Yeah.
yes. Good evening, sir.
Good evening, everyone. So we'll get started. I'll share the screen.
Hello.
Yeah, Divya, just
Yeah.
give me a moment. I'm sharing.
Okay. Okay, fine, sir.
Okay, so that's the best I can do. I hope you guys have already listened to one of my sessions on linear algebra, right? Type F in the chat box if you have already listened. Yeah, thank you. Just to make sure. Oh, there are people who have not joined. I don't know. Maybe you have missed that session. Okay, so anyway, we don't really need that much of linear algebra for this. Uh, we will look into this topics for today's discussion, which is introduction to data science, machine learning, and artificial intelligence. Okay, so I'll change my. Okay, is it better enough? Rahul and Vinay? Yes. Okay, so we'll get started with, like, we have two parts in today's session. The first session, the first part is this introduction to data science, machine learning, and artificial intelligence. The second session would be on simple linear regression. Okay, so the plan for the first part is as follows. We will talk about what data science is. We'll also give a notion of what types of data or information is available. We will talk about various domains of the data analytics or data processing. We will define what machine learning is, and we will define what artificial intelligence is. If time permits, we will talk about the big data part in this, which is kind of extra piece of information that I would like to talk about. Right. So we will briefly cover up on these things. Why do we need machine learning? What are the different types of machine learning? And what is a typical workflow of machine learning implementation or development of an algorithm and implementation, use cases of machine learning. We'll also touch upon what is supervised learning and what is unsupervised learning in this first half of the session. The next half, we will talk about one supervised learning technique, which is linear regression. So, well, let's get started with what is data science. I think you might have already researched a bit about what is data science. it basically use raw data along with statistics and machine learning techniques to draw some conclusions about the data that we are looking at and use that for the decision making in day-to-day processes that you are interlinked with for either your work or some personal decisions that you wanted to make and so on. So when you are looking at obtaining some useful insights from data, there are several things that you have to do to obtain this. So the activities that are included are basically when you receive the data, you have to look at the data, that means inspect it, clean it. If there are some missing values, if there are some outliers, you have to identify them and then clean them. And we have to get to the data that can be used to build a machine learning model. Get to the form that it can be directly used for building a machine learning model. And then the next part comes is the modeling. And once the model is developed, you should use it for making the predictions. That's the usage of this. So the whole steps that we have talked about are parts of an exercise that we wanted to use data analytics. We could just divide them into a couple of analytics processes, which are the following. So the process of inspecting, cleaning, and transforming falls under the arena of descriptive statistics. That means you wanted to understand what data is, what is the relationship between the various attributes that are there in the data, and so on. Or there are any outliers in the data. How do you impute the missing values? Basically, cleaning the data. That's what we call as descriptive analytics. And the second part where the modeling, the model building and predicting involves is what is known as predictive analytics. And when you use this model to do recommended actions or get the business insights or use it for your own problem, that's where we call it as the prescriptive analytics. Why is it prescriptive? Because you are suggesting that this is the decision that you wanted to make based on the model that you have built. So in order to better understand what kinds of machine learning algorithms and so on, it is essential for one to know about what are the different types of data that one generally encounters. There is a question from Manjunath. Hi sir, prescriptive or predictive, the steps which are saying, so predictive stops at the place where the model is generated, and the prescriptive says, how do you use this model for your case? I hope that answers your question, Manjunath. Right, so we will look at the different types of data that are available. Generally, we call them, categorize them into such divisions because certain types of data are amenable for basic machine learning techniques, and certain kinds of data are more amenable, or we have to do the neural nets based, the artificial neural network and the deep learning based machine learning. We will talk about what is AI and how are this AI, ML and deep learning related in a while from now. Nevertheless, just look at the types of data information that we generally encounter when we wanted to build machine learning models. So the first type of information is a quantitative information. That means it's a continuous variable. Continuous variables. So if you look at the temperature, blood pressure, pulse rate, yeah. So that's kind of information that we are looking at. That's a quantitative. That means it is a continuous variables. Okay. And we can also think about as this numerical continuous variables. Okay. These are the numbers that we encounter. The other types of variables that we encounter or the categorical variables. We would say a person X belongs to this class of non-diabetic or class of diabetic. A person X belongs to class of normal weight, underweight, or overweight. What we are trying to do is we are trying to put a label which is a categorical variable, which does not carry a numerical value, but it is specifying a class or type of particular data. Okay. So the other thing is the textual data. This is basically the documents, manuals, or notes. Of course, this also covers yes, I know that Janakiram, but I have to see this chat box so that I'm like, I want you to, yeah, so I have already discussed this logistics before. Yeah, so that it would be a live discussion instead of just a one-way teaching. Right. So the text documents, this also covers what are the known as the social media tweets, which are written in text, right? Facebook or comments. Yes, there are. So all of them actually fall under what is known as the text analytics domain, where the text data is analyzed and then try to find out some information from them, such as what do you do as sentiment analysis, right? So that is another type of works that we could do. Yes, blog post also comes under this because you see that's a mixture of data. Some blog post also contains some pictures and so on. So nevertheless, if you're just looking at the text, that's where one of the informations or data types that are coming into picture. So other types of data that you could encounter are audio signals. Yes, it can be part of it, but when you are doing the NLTK, you just generally, if you wanted to get some insights about the sentiment analysis, also you generally remove all of this and try to understand from the text itself. Manjunath. Of course, there are a lot of people who actually put the symbols, right? So I'm happy, they will put a smiley face. I'm angry, I'll put a very red face saying that no, I'm angry. So generally they do that. But when you are doing analytics, they actually remove all of that and then try and get an insights about it. So what was your question? Language translations. Language translations, I think it has much more to deal with than the text analytics itself. Subhash. Yeah, the other type of course, the speech signals can also be part of language, because when I'm speaking, and you can ask actually Google or Siri to translate it. I don't know whether Siri has this facility, but the Google can do it. So you talk about something and say, it will reply in an audio signal that what is hello in some Spanish, it will tell you the Spanish word of that. So it is not just the textual information that is being processed there, it is an audio signal that is being processed there, and you are getting the output, right? I hope that you got a grasp of what, yeah. So the speech signals can also be a part of this audio translations or language translations. Of course, text translations, I'm not sure, because text translation does not only involve the same text that you have given, but also involves some grammatical rules that are needed to be followed for each language and so on. That's more complicated than just looking at a text and talking about the sentiment analysis and doing the NLT. Okay. So the other type of images, the information that we get are images, which are basically the pictures, fingerprints, handwriting images, and also videos. All of this come under the multimedia information. So what do you mean by Google Lens? It is capturing the images and then trying to look at, that's an unsupervised learning algorithm that is sitting backside. We will talk about that when we discuss in unsupervised learning algorithms in general. So we are not going deeper into this details of what they are. I'm just trying to put what kind of information that are available when we are looking at the information that we generally deal with. So I think this is the major categories of data that we generally look at. So what kind of this is overall structured and unstructured, right? This combines both of them. Good question, Rajshekhar. So the quantitative information along with the categorical information, these kind of forms fall under this structured data, and the rest of them will fall under the unstructured data, because you'll be able to obtain such information in a form of matrix, as we have talked about in the linear algebra session last time, where the features are represented in the columns and the number of samples are represented in the rows. I hope that answers your question, Rajshekhar. Kindly confirm that in the chat box. Yeah. So based on what type of data you are processing, the data analytics has been divided into certain domains. And based on that domains, what kind of machine learning algorithms works well for that domains are decided. So let us now look at what kinds of different domains are available in the data processing and data analytics. The first one is the quantitative analytics, where you are processing the quantitative data. The basic types of machine learning algorithms that are coming under this is this small machine learning algorithms that we talk about. Basically, we will discuss this more. This is general machine learning algorithms that when we say machine learning. So when you look at the images or the videos as the information that is needed to be processed, then we are talking about a domain which is known as computer vision or image analysis. So that's where this another branch of data analytics, where it particularly deals with only the image information and the videos, basically the multimedia types of information. This is another area that is divided for the analysis differentiation. So we will look at why these domains are divided in such a way, and what kinds of machine learning algorithms generally work for this domain, and what kinds of machine learning algorithms should be implemented in these other domains, and so on, as we go along. Okay. Yes, the image processing and all these things comes under this computer vision, Joomla. Right, the next domain is natural language processing. This is where we are talking about the sentiment and analysis, the textual information that is there in the books and so on. If you wanted to process that and then do analysis on that, which is basically the textual information, then that domain of data analytics which deals with them is natural language processing. Of course, the audio also falls under this, as we have just discussed. Yes, quantitatives for the structured data. Word to vectors, all of them are falling under this natural language processing, Sai Charan. I hope that answers your questions, Vinay and Sai Charan. This is the domains. As we go and discuss, we will see that the general machine learning, as it is covering all, is 3 anything for census as well. As it's covering all, is there anything for census as well? Census, I am not able to grasp your question. You mean some, so this one, we can do the sentiment and analysis and just talk about what are the people. So what are the topics that people are talking about mostly in the Twitter and so on. That's where we, so how viral is the news and so on. Human senses, anything. So of course, the images, data processing domains, anything which covers human senses. No, I don't know. So when you touch something, if you could transfer that into some electric signals, then maybe there is a possibility. But as of directly sensing, processing the Somehow you have to get it to the either textual, the structured data or the unstructured data to get something out of whatever you wanted to analyze. I hope that answers. We will talk about that. We will talk about that, Janaki Raman. We will talk about that. What are the things that we are looking at? Medical data also comes under these images. You see that, right? You right away see that. So if you have the images of the people, that falls under this image processing or this. So when you look at typical process history data, that's a structured data. You know what variable and what time what variable is. So let's say you have temperature, pressure, density, viscosity, or any other parameter of the process that has been recorded. You know them, and it has been recorded in format of either an Excel sheet or a CSV file, something which is structured data. Mahadev, I hope that answers your question. So that's a structured data, and a typical general machine learning algorithms can be applied directly for that. Right, thank you. So where are we? Yeah. So if you look at typical data analytics workflow, so we will just talk about the steps that are involved in it. The data, we have to read it. We have to curate the data, that is for the model building. So when you say curate the data, that means you are looking for checking for duplicates. Is there a repetitive data? Is there any missing data that is available, or all the attributes that are there? Yes, we will. Yeah, I am going to put all of them and say this is going to be the exploratory data analysis. Nitish. Yeah. So if you wanted to actually transform some of this data, you could do that. The data manipulation. We can fix the outliers and so on. I can turn off the video if it is blocking the portion of this. If I switch to the full screen, then I cannot read your comments, right? So that's the reason why I have to have them. Okay. Otherwise, I feel that the class would be just one way. I will not be interacting with you when I'm teaching. That's the reason why I have your comments on the right-hand side. I'm not sure. I haven't heard about this Batten cuckoo algorithm. Okay, you mean to put that slideshow and then also let me try. I want. See, the problem is this portion would be blocked for you. That is the thing. Do that. So you cannot see the chat window. Only I can see it. Everything in the slide is visible to you. But there is no chat window appearing. You can move it. Okay. I have. Okay, so this is a typical data analytics workflow. So we will check that is the integrity of the data. That means you curate the data. we would take that question, Mahalingam, later, because we are not actually discussing about which software is better. We will discuss this out of the class. Okay. Right. So we were at this. Portion now. So the data manipulations will be done such that if you wanted to transform, if you wanted to look at and transform some data, let's say x1 square and so on, this is where you can manipulate the data. And then the other step is summarizing the data. If you have numerical data, you can say that how much is the spread of the data, how much is the data following some distribution and so on, so that you can characterize the whole data in a nutshell, so that you can understand or you can explain it to your clients that this is the data and this is the nature of the data. You can also do a visualization if the features are in the one or two dimensions. That means if your number of independent variables are only 2 or 3 dimensions, you will be able to visualize the data and so on. The next step is the data cleaning. If you wanted to look at the outlier, are there any outliers, and there is a segmentation that we need to do, and the build models for those segments separately and so on, you can do that. Okay, so the next step, once you get the data that is amenable for building machine learning models, is to build models and then check the performance of the models and collect more data if it is needed. Okay, and then last step is deriving insights from the data and recommend actions. So what is this descriptive analytics deal with in the whole thing? Whole part is basically from here to this part. This is what the descriptive analytics deals with. So that's what we're going to see. How can you understand your data? That means you have to come up with better ways of understanding your data. That means instead of presenting whole data to your client or manager, can you summarize the data such that in a nutshell, he will understand those things or not, is what we are looking at. Okay. So can you explain, that's what I'm talking about. Can you explain the data in a nutshell instead of showing the data to him? Okay. How do you test for the integrity of your data? You are able to identify if there are duplicates, if there are data from different sources that are measured incorrectly or correctly. Are there any missing data? Are there any outliers? So if data is multidimensional, that means if it is having more than 2 or 3 attributes, how can you actually bring them to lower dimensions so that you get a visual feel of the data? How do you plot this data and understand if there are any patterns that you are able to see this? All these things are dealt with this descriptive analytics. So other things that descriptive analytics deals with are exploring the relationship between the variables. That means why you take data cleaning after visualization. You can see who is stopping you. You can just plot the data that you have received as it is also, right? It's for the, yeah, I've seen that. I got your question. Ajay. See, the part of it is, okay, maybe I just not call it as data cleaning. I would say segmentation or outlier detection. Then if this heading itself is your problem, the reason why we do the segmentation is the following. Instead of building one linear model for the whole data, if there are different segments that are there in the data, can you build one model for each segment? That would be enhancing your model accuracy, because that particular model is specific to that particular segment. That's the reason why we wanted to do this segmentation, to understand if a single model for a whole data works well, or should we do actually different models for different segments in the data. That you can, after plotting only, you will be able to see that segments if they are available or not, isn't it? I hope that answers your question. If the heading itself is a problem. I hope you get what I was trying to do. If it is a problem with the heading, that's okay. Yeah, so this is all the descriptive analytics deal with. Basically, we are looking at another problems that the descriptive analysis also deals with is, are there any relationship between the variables in the data? Is the data following certain distribution and so on? All of that questions could be answered by statistics, right? So also we have seen in the last class that if there are any linear relationships between the attributes, we could be able to use some concepts of linear algebra to understand the linear relationship between the data. Okay. So what is inferential analytics? This is important because this we haven't talked about in the previous types of analytics procedures that we have talked about. Inferential analytics is something important from the statistics, because all the times you might not get the whole data for your analysis. What you have is maybe a part of the data, which is also called as sample data. So the question now is, what inferential analytics deal with is how well are the inferences made on the sample data is applicable to the entire population. That's where this hypothesis testing and all the things that are coming to picture from the statistics in the inferential analytics. So that's another part of, because we are talking about the relationships among the variables and so on, this will fall under the descriptive analytics. Okay, so what is predictive analytics? Now I have talked about it. Predictive analytics talked about, predictive analytics is building about the models from the data. And last one is the prescriptive analytics, where yes, you can analyze because you are actually looking at the relationship between the data. Of course, this is a part of, because you wanted to check it, right? This can be part of the predictive analytics also, because you wanted to know, you can look at either in the descriptive or predictive, Subhash. Okay. The other last one is a prescriptive analysis, where you use this model for your problem case that you are working on. So that covers whatever things that we have discussed in the workflow of a data analytics, right? So now let us well into the next part of today's session, artificial intelligence. So what is AI? I think you would have already seen several definitions and so on. It is basically intelligence which is mimicking the human behavior. So if you look at Siri and Google, if you ask a question, it will reply as if another person is replying. Of course, it is not as matured as the person's reply, but if you ask for information, it has been trained by several algorithms and data that it could answer your question to the best extent possible. If it is not able to answer also, it will say, sorry, I'm not able to answer that question. Do we get sampling data, or it's majority of getting incomplete data? So it's not an out of box question, Ajay. So you will get, what you get is a sample data only. So basically this is what is AI, right? So how do machines achieve them? How are they able to reply to your questions? They are able to reply to your questions because they have learned something from the information that has been given to them. So what are the different types of learning that are available? We have kind of supervised learning, unsupervised learning, and reinforcement learning. I'm not sure whether your sessions have parts of this reinforcement learning because it's a little advanced. What we generally cover in this course is basically different supervised and unsupervised learning techniques. So how is it what we have understood from the previous slide is machines are learning from the data that is being presented to them. What is machine learning then? That's what, because machines are learning from the data that is being presented to them, because it is learning, we call it as a machine learning. Okay. So machine learning is a key component for the AI to work, because in the artificial intelligence, you have to make the machine learn, where the algorithms that we are going to propose helps in the machine to understand, make the machine to understand that. So you say that MI as an integral part of AI. So we have the machine learning as an integral part of it. If AI has to work, then we have to train the machines. That is only possible through the machine learning. So basically AI, ML is a subset of AI, because you wanted to look, if you wanted to have AI, you should have ML, right? Now, what is this deep learning and neural nets and so on? So the difference between the classical ML and the deep learning is the following. The major difference is how much of human interference is required in giving the features to the machine to learn from. Okay, so the classical ML and the deep learning strategies vary in this aspect. So if it is not clear, I'll just give some examples so that it will be clear. So what is the difference between classical ML and the deep learning is the following. In machine learning, as we were talking about, we will give the attributes and also the labels if it is a supervised learning to the machine. Okay. In deep learning, what you do is you don't handpick the features for the machine, but you would just give an image or an audio file or a video file. And the task there is to extract the features directly from that image or some other multimedia thing that is there. That's the reason why when you look at image processing and computer vision and natural language processing, you don't give the attributes, you don't give the structured kind of data to them, because they are all fall under the unstructured data. The task of extracting the features also, X1, X2, X3, and what would be the label for them and so on. No, it is not. It is not. So the task itself is taken up by the machine. So that's the only difference between the classical ML techniques and the DL. So we will talk about it. Yes, we will get to that, Janaki Raman. Okay, I will just close the chat box. Basically, human intervention is manipulation of data, but DA, no, human intervention is not. So yeah, you are manipulation of data and so on. We are not doing that. We'll get to that. So so what we are doing is, are we giving the features X1, X2, X3 to the machine learning model directly, or you just give an image and asking them to extract itself? Is what is the classical difference between the ML and the DL. I'll show you some pictures that will make it clear. Okay. So what deep learning is basically deals with is, it will try to extract the features by itself. Okay. You are not giving X1, X2, X3 from the data presented to it. Basically, the typical data that we give them is the image data or the videos or the multimedia data. So you could study more about that in the following link of the IPM, which will be available to you once you receive the slides. So some more differences. I'll show you the final workflow of the DL and machine learning, so that you will get understanding. Yes, the DL can figure out the features by itself. Sai Charan, you got it right. So the machine learning algorithms can provide answer or decision. Okay. They only explore data based on the programmed feature extraction, that only look at the data we program to do some. So let us take an example of linear regression. Okay. When we call that linear regression, what happens is, it will try to find beta naught and beta 1 that we are going to see by optimizing a function which is known as sum square errors. And this optimization program will be called when you run the linear regression function in the Python. So basically all of this is already coded by you. So when you call this, all that functions that you have written will be getting executed. This optimization problem will be solved and you will get this beta naught and beta 1. Okay. So there is no notion, other difference is there is no notion of neurons in this classical ML techniques. We don't use artificial neurons in this classical ML techniques. Examples of classical ML techniques are all of them except, so we can talk about the supervised learning examples and unsupervised learning examples. The things that you are going to study mostly in this course are based on this classical machine learning techniques, not the deep learning techniques. Yeah, we will get to that. So artificial neurons are the imitations of the biological neurons that would help the network to learn something from the data that is being presented. So I hope that answers your question. It's not a physical component. Okay. Manjunath, does it answer your question? So what is difference in this deep learning is this class of algorithms that can learn on their own. That means these are deep learning algorithms. When we expose the algorithms or the different situations or patterns of the data, these algorithms adapt. So basically the language processing, the natural language processing, the audio processing, all these things uses this. It is not exactly, but you could think about it as a mathematical form. So that's where the activation form of this artificial neuron comes into picture. There are again several types of activation functions that can be used in a neuron and so on. Yeah, you can just think about that as mathematical form of biological, but it's not exactly the mathematical form of a biological neuron, but the structure itself says that this is a neuron. And when you think about a brain, it has several neurons connected in a network. That's how it forms. Because there are several neurons, artificial neurons that is connected. This is called artificial neural network, ANN. So that's the relation between the biological neural network and the artificial neural network. So the best part of this deep learning algorithms is these algorithms adapt. That means they can learn on their own. If you present a new picture to the AI based or deep learning based algorithms, the more pictures it gets, the more it does its processing on by itself. That means it extracts features and then learn on their own and then update its learning by themselves. But when you come to the classical machine learning algorithms, it is based on the data that you have given already. And if you wanted to build an updated model using the more data, you have to, schedule that and then build it and then check, verify it. All of these things has to be manually done, which, yes, facial recognition is a part of example of deep learning. So what is this deep learning is? Basically, it's uncovering the features in the data. We never specifically programmed them to find. But here we have to tell what are the features. So that's the reason why we say that they learn on their own. We cannot think about the deep learning without a concept of artificial neurons. But in this classification, the classical machine learning techniques, the concept of artificial neurons is not at all there. So there are two major differences. The way the features are generated. So for a classical ML, the features you give them, and then the models are built based on the functions that you have already written. That means you coded how the model has to be built. Nevertheless, in deep learning, that is not the case. These features are automatically generated and the models will be built directly. Also, they are adaptable. These are the things that are differences between the except ML and DL, what are the other subsets of AI? No, most of the things that we have covered falls under these things only. So you put anything in the either umbrella of ML or DL, and you see, I'm going to show you a picture which actually shows a relationship. So, and we can also learn from other mature deep learning models, as the deep text, they will always be part disadvantage since they don't have time and available to train. Yes, the other problem with this deep learning things is you need enormous amount of data, and also training this deep learning models is bit tedious. Is ML a supervised and a DL unsupervised? Not always. This is machine learning techniques. Also, we have unsupervised learning algorithms, and the DL there are supervised learning algorithms also. So it is not always correct to say this statement that what you have written. Game AI, where does it fall? I am not sure what is game AI. I haven't heard about it. There was some comment. Other mature deep learning. Yeah, so somebody has commented about it. I think it is Nitesh. Yeah. So the problem with the deep learning models, the flip side is the training deep learning models involves a lot of computation and the cloud space and so on, because the data can also be dynamic in this case. This is the problem with the deep learning, whereas this one we can build on the normal. I'm not sure. I really don't work in those domains. Maybe you can just check it, Subhash. I don't want to give any answer without knowing. I'm not sure. I hope they would be based on AI, but I'm not very sure. Okay, so this is a pictorial representation of a difference between classical machine learning workflow and the deep learning workflow. Take a minute to just look at these steps that are involved, and then you'll be able to appreciate what we have just talked about. And this has been taken from this particular journal article, which is AI applications to medical imaging from machine learning deep learning. So the thing that you have to observe is, so we have medical images. If you extract the features by yourself, okay, and then use the pre-processing, and then you select the features and then build a predictive modeling, that is what is known as a classic machine learning approach. When you're using the deep learning, you use the medical images and the features are extracted by a convolutional neural network, and you can fine-tune this convolutional neural network, or you build ML models based on that particular features, and then you use them for the prediction. Okay, so if you just look at this, classical machine learning with various processing steps involve handcrafted features. That means you have to define what features are and then give it. Okay, and in the deep learning, deep medical image feature, we have to, so you just use the images, and the extraction of features is also done by some neural networks, which the example thing that I have been shown here is a convolutional neural network. I'm not going to dwell into what is a neural network, what is a convolution, because that's another full thing. Okay, the term deep learning, but I would like to talk about why is it called a deep network is basically you have some features. So each neuron input, this is the input layer. How does it look? I'll just draw a typical deep learning framework. So you have features that has been extracted from this thing. Okay. Yes, and that also includes increases the training time as the networks get deeper and deeper. So the last layer is an output layer. Okay, and how many layers, the layers which are in between this input layer and output layers are I haven't worked on textual analytics, Ramendra. You could figure out. I'm just giving an example to illustrate or get your feel for what is the difference between the deep learning and the ML. Ramendra, yeah. So these are what are known as hidden layers. The more the number of hidden layers, the more deeper the network would be. That's the reason why it is called as a deep learning. If you have only one, then they are called as certain. So for example, the autoencoder that we will talk about when we are talking about the unsupervised learning is only having one input layer, one hidden layer, and one such a artificial neural network layer is known as perceptron. So there are several things that we cannot really dwell into this thing, but I want you to, the major goal here is I want you to get a feel for what is difference between the classical ML and the deep learning frameworks when you are looking at a problem. Right. So you might think that machine learning and deep learning are drastically different now based on this thing. The whole goal is same still. The core point is still to train a machine to learn from the data. Okay. That is similar in both ML and the DL. Okay. What is layers extraction? So here you have to manually get these features from the data and then give it to the model. That's classical ML. Here what happens is the algorithms themselves will get these features and then used in the predictive modeling for the machine learning. So that's the difference between the classical ML and deep learning. Vinay. Right. So we are still looking at the core point that either you use deep learning or ML. The whole point is to make the machine learn. That core point is still intact between the deep learning and ML, DL and ML, right? So basically, if you look at AI, it's as a big picture. For AI to work, ML should be there. And deep learning also involves some kinds of techniques to help the machines to learn. That's the reason why we could take it as a subset of the machine learning problem. So that brings us a relationship which is given in this slide there. If you are looking at AI as a big picture, ML is a subset of it, and DL is also a subset of this ML. That's the reason why you can always visualize DL as a subset of machine learning. I hope that there was some question that was asked. Is still the DL is a subpart of ML, or some question related to that? Yes. Yeah, Janaki Raman, you got it right. So that's the reason I asked you to wait, because I'm going to talk about it. So pictorially, that what we have seen here, AI is a bigger thing, which will work only if there is an ML, and DL is a part of the ML. Okay, so that's how you should visualize what AI, ML, and DL relationship. No problem, Mayank. Okay, this is all about the AI and this thing. We have talked about the predictive analytics. In predictive analytics, we wanted to build models depending upon what type of data you receive, whether you receive a labeled data or unlabeled data. We have two types of problems, which are the supervised learning and unsupervised learning. And in this also, I think we have discussed this. Anyway, I'll repeat it. If Y is a continuous variable, then we have what are known as the regression problems. If Y is a qualitative variable or a categorical variable, then we have what are known as classification problems. The predictive analytics deals with building the models which takes Y, which represents Y as a function of this attributes X. If Y is a continuous variable, we will get what are known as regression problems. If Y is a categorical variable, we are dealing with what are known as the classification problems. Is that part clear? Type C in the chat box if the difference between the classification and regression problems is clear. Okay. So what does also this predictive analytics deal with is the model building part, as we are always been talking from the beginning. The model building part is major step in the predictive analytics. Okay. As we have seen, we can build the models using either the classical ML techniques or the deep learning techniques. The classical ML techniques have an advantage that you could build the models quickly. The deep learning techniques need different frameworks and also compute to train the artificial neural networks to work for you. And most of the tools that you are using from Google are built on this deep learning techniques, which they have the compute power and the cloud space where they learn all of these algorithms, and they keep on evolving as and when they see the number of data that is there. If I am using Google Mini and I talk something about it, if they don't know how to react to that, they will record and it will see what could be the responses in the background that could be possible and so on, like this. The more the inputs it receives, you see now you can realize how many people are using Alexa and how is it getting trained and how is it getting better and better with time. So that's where the deep learning techniques are adaptable means. Okay. So when you are trying to build the predictive models, we are only looking at a supervised learning approach because we know the labels and we wanted to use, if the test data that comes, we have to predict what is the value of Y in case of the regression problems, what is the class of Y in case of classification problems. The unsupervised learning techniques cannot build the predictive models. So the other question that is there in your schedule is, why is ML needed? Okay, so now we are hitting around 9 o'clock. So this should have been completed by 1 hour. Because we are running late of time, maybe this session might get extended by half an hour. So I'm just, whether autonomous car technology is deep learning for prediction. I don't know whether there is a prediction or not, it will learn. So it is, yes, deep learning. There should be some form of deep learning. Okay. So why is machine learning needed now? Because as an organization, somebody wants to use the data and then use it for any of the business decisions that will help them to improve their profits. Okay. So if you are looking at data that is coming and newly added, and if you generate the machine learning models, if you are looking at the deep learning framework such as this, networks or algorithms, they work on the background and build the relevant models. Oh, what is reinforcement learning? I told you. We are not going to cover it in major, but I'll just give you an idea. So the reinforcement learning actually puts a learner in a situation. Okay, let's say the checker box example of the chess player. What it does is it will put it in a environment E. Okay, and then according to the move it makes, okay, it will make a move. According to the move it makes, it will be given a reward. If a reward is positive, it will learn that that step is good step at that particular location. If the reward is negative to that, then it will learn that, okay, this step is bad, I should not make this. The more and more it learns, this plays this kind of games, it learns what is a good move at what position of the game and so on, and it will become bigger and bigger and learns much more, and then it will be at some point beating. So these algorithms, the examples that have been quoted for the AI and so on, falls under this kind of. Yes, we can use the DL for prediction also. Okay, I hope that answers your question. Somebody who wants to reinforce. So reinforcement learning is completely a different frame of learning where a learner is put it in a situation and then based upon it moves, it will be given a reward. Based on the rewards it has been given over the time, it will learn whether I have made a good moves or not. All these things learning will be there. And when you encounter a new situation, it will try to work in a way that, yeah, so that's the reason it would be a little over the head, Sai Charan, because we are not covering it in a detail, the reinforcement learning. So as new data gets active, how frequently we need to tweak the models. That depends upon what application you are looking at. If you are looking at the regression models to find out the stock problems, maybe you might have to look at every day or a couple of times a day. I hope that answers your question, MS Mahalingam. Yeah. Depends upon your application, how fast, how dynamic is your process. Please. Okay, so this one I think we have already talked about. We have supervised learning and unsupervised learning. Supervised learning, we have to give data that in the form of the attributes and also the label that the class or the output variable is. So some data which is correct data has to be given to the machine learning to learn from that, and then when you give a new test data point, it will use that model to predict what would the value of y is, or what would be the value of what would be the class of that particular data. What is unsupervised learning? We don't have that attribute value, that the data that is what is known as unlabeled data that is being given to that. There is no notion of dependent and independent. I think we have talked about this. So what we are trying to do is basically, can we cluster the data into some groups and then build some supervised learning models for them. So the first part is the unsupervised learning, and in the second part, if you have the labels after separating them, then we could talk about the supervised learning, and such framework is known as the semi-supervised learning, because first unsupervised learning is used, and then based on the unsupervised learning categories, you would be able to use some supervised learning. Oh yeah, we will talk about this unsupervised learning. Examples are there, Sai Charan. As we go along, we will see that. Of course, the image recognition is unsupervised learning, because we don't know a priori what are the features and what is the output variable that is there. Just tell you, right? So this is unsupervised learning. And unsupervised learning, as you know, there is no notion of model and there is no predictive power for this. What you are trying to do is you are trying to cluster the data of similar features into one cluster and then use it for your analysis. That's all the unsupervised learning algorithms does. And how much clustering can we do classification using unsupervised learning? You cannot do, Ramendra, unless after doing the unsupervised learning, you have to label those clusters separately and then build a supervised learning model on top of it. Then only you can do that. Ramendra ji, I hope that answers your question. So that's the disadvantage of the unsupervised learning algorithms. So this is the use cases that of machine learning. Classification and clustering is same, sir? No. So major difference is the data that you would like to use for classification and clustering. Classification, you will receive the data of this sort. You will receive the features and also correct output label. But for the clustering, you just receive this data. Based on the similarity of the samples, this would be clustered into groups. That's the difference. You don't use the information about the labels. You don't have that in the clustering case. Okay, but in classification, you have that. So there are several use cases this machine learning can be put into health, retail, and financial. I have just given what are the use cases in each, what are the examples in each cases. Thanks, Sachin. In each cases, this machine learning can be used as. In health, majorly you use it for the diagnostics. The retailer or e-commerce thing, we would use them to build the recommender systems. Stock market, auto trading, we were talking about this, I think, for the Mahalingam's question. In the financial, other financial institution, banking, we would like to classify the customers into potential customer for giving loan or not. Such kind of applications are there. I'll anyway show you a few use cases here. Okay, so this is a difference between supervised, unsupervised. I think somebody have also asked about the reinforcement learning. I hope this might help those. So what is supervised learning is basically you give the images and also the training data. That means X1, X2, and also the label. That means this fellow has some problem, and this image has images along with the labels. You will give them. That means you will give the correct labels also, whether such fellow has some problem in the brain or not. That data you will give. If that is that, a label data set is provided. Learning is task driven, immediate outcome or prediction. RLP uses this banking algo for customer to give learn. Yeah. So they do that. Most of the organizations do that. Okay. So this features you could extract. If you give that would be classical machine learning. If you don't give the features, that would be ML model. So deep learning, and you extract the features and then use it for the diagnosis. And then when the new data comes, you will say that whether this is this person's this MRI scan of brain is okay or does it have any problem. We would like to categorize them. This is a typical classification example of a supervised learning algorithm. Okay, somebody have asked about unsupervised learning example. The answer is here. So the major thing is you don't have labeled data. So learning is based on the pattern identification recognition. If you have data of several patients, okay, that you have the features X1, X2, X3, X and so on. Okay, and now we wanted to categorize these patients into clusters based on the features that you are giving. So we would say that there are so many different types of patients that are there, and we would separate them, and we will not be able to say who are having a disease and who are not having a disease, because the clusters. Clusters are homogeneous. What do you mean? This need not be. You can see that there is only this cluster is big, this cluster is big, and this cluster is small. You don't need to have always homogeneous clusters. When you say homogeneous cluster, that means basically you are looking at all the clusters will have same kind of variance and so on. It is not requirement. Lakshmi Narayanan. Yeah. Supervised learning can fail when you pass something which was not seen or observed before. Yes or no, depends upon how good your model are. But you will get a, if your model is good, you would get a reasonable. The whole point is that, right? Because you don't, in the test data, you don't actually send data that is not been seen. That's the whole point. It should work properly if the model is good. Clusters are neighborhood of particular data point. There are several different clustering algorithms available. We will talk about one such algorithm, K-means algorithm, when we are dealing with this unsupervised learning class Sai-Charan. Maybe that has it will be scheduled sometime later. Okay. Yeah, this is reinforcement learning. Okay, so whether a particular drug works or not, with the reward or punishment before repetition, what does this algorithm do is it learns or acquires skills to make decisions. Patients and their medical history, if it is given to you, if you give a new drug, does it have any side effects? Okay, then it would be taken off. If it is some side effect is there, if side effect is not there, then you will not give a negative reward to it. If side effect is there, you will give a negative reward to it. Based on that, it will learn what kinds of medicines are available are good for patients of certain category and so on. So that's the framework. We haven't dealt with the reinforcement learning in detail though, because it is not part of this, but is there any example to use case regression algorithm under supervised learning? Yes, we are going to look at one of such cases in the next session. I mean, next part of the session. Right. So this is the use case of health. We will talk about the other use cases when we are talking about the unsupervised learning. So these are the different types of machine learning problems that used for decision making. We have talked about the classification problems. These are what is known as linear classifiers, because you are trying to classify two different types of classes using a linear classifier. Okay, linear separation, linear decision line. And if you have three different classes like this, the dots are two different classes like this, but when you have a linear classifier, you have three classes here, right? So when you have a linear classifier, you might not be able to classify them simultaneously. Maybe you have to build two linear classifiers which classifies each of them, or you should go for a non-linear classifier. So these are what are known as classification problems, and the function approximation problems are the same thing. We wanted to represent y as a function of x. What function form you choose to model will decide whether it is a linear regression problem. This is what is known as linear regression problems. And if you choose a nonlinear function to model this, that is nonlinear function, nonlinear regression problems. And if these terms are very, very new and it is confusing, all we are trying to do is a curve fitting in your Excel sheet. Okay, that's also an optimization problem. When you are looking for a model which is a linear, then it is a linear regression problem that is being solved there. And when you are looking for other forms of these things, then what are solving is a nonlinear regression problem. But Excel is solving it for you and gives you a parameter values a0 plus a1x. We're having a single attribute, then it will give you this kind of model. That's a linear model, right? Y is equal to mx plus c kind of model. Okay, so these are the different types of problems that machine learning is used to make decisions. So what are classification problem examples? Fraud detection in the credit card transactions, identifying whether an email is spam or genuine. Okay, do we decide from visualization if it is linear? You can, that will give you some thoughts if you are able to plot it. If your attributes are 2 or 3 dimensional, you might be able to do that. If it is more, you will not be able to plot it, right? Of course, we can do a scatter plot and then observe the relationship between different variables. That is also can be done. We will not be able to do that always if the dimensionality is high. That's the reason why we wanted to know what is known as the dimensionality reduction techniques. And we will do some feature engineering using this dimensionality techniques. Otherwise, we need to build all possible models. Yes, if you are not able to visualize, even the dimensional reduction techniques does not help. In most of the cases, this helps. Dimensional reduction techniques help. And then when you build a model using the reduce or transformer dimensions, and then you can come back to that. So yeah, you will get better at it. Yeah, you will do all possible models and then see which is better. Correct. That is also there. Okay. So detecting defective and non-defective items. That means these are all the examples of the classification problems. You can just go through it. Okay. So what are the examples of Mahalingam ji asked, right? So what are the examples of regression problems? Function approximation problems. These are all function approximation problems. Predicting materials property for different molecular structure. Okay. Predicting the reaction rates from the experimental data. Predicting scores in a cricket match. All these things are the regression problems. I hope that answers your question, Mahalingam ji. There are several use cases of regression. Function approximation problems also. Okay. Okay, these are all different machine learning techniques that are available. So linear regression, that's what we are going to talk about in today's next half session. There are algorithms for the classification. There are unsupervised learning algorithms. An optimal trajectory planning be a regression problem. That's a control problem. Optimal trajectory planning. No, it's kind of, you could pose them as, I'm not very sure, this is a control problem. You're trying, you're trying to have an optimal trajectory planning. I'm not sure whether it will fall. There is no decision making in it, right? So basically, machine learning deals with problems where you wanted to make prediction, build model, and make prediction. So maybe if you are from a control background, you would have heard what is known as model predictive control. That actually talks about this control problem, which is, so the idea is you would have a horizon. I think it is going a little bit off from what you're talking, Suhail. We can talk about it later because that is not relevant to all the people. I'm not sure you could pose it as a regression problem, but it is a control problem which you could solve by using other techniques in control, which are the model predictive control, for example. I hope that's a short answer for that. Yeah. Okay, so there are several different algorithms, and just make a note of these things. You are going to see some of these algorithms as the classes forward in the course. Okay. This one is one of the dimensionality reduction techniques, principal component analysis, and linear discriminant analysis, which can be used as a classification algorithm, but it's also does this dimensionality reduction. Okay, so there are several other algorithms that are there. Okay, we will stop this session here. I would skip the rest of this because we are running out of the time, and we will take a quick 5 minutes break and then come back with the session on the linear regression. Okay, so time is 21:28, so we will be back by 21:33. Okay, the time is up and we are back. Type C if you are back in the class. Chat box. Right. So let's get started. In this session of today's discussion, we will talk about linear regression. We will talk about different types of linear regression and we will restrict ourselves to a simplest form of regression, which is a simple linear regression. So because, is it better now? Yeah. So just check your speakers, Ravina. I haven't modified any settings. Okay, so we are talking about a supervised learning technique called linear regression and what is a step-by-step procedure for doing a linear regression. Because we are talking about supervised learning, I hope you all already know that what is the difference between supervised learning and unsupervised learning. The major difference is the data that is given to you. If it is labeled, then we are talking about the supervised learning case. If the data is unlabeled, we are talking about the unsupervised learning case. Depending upon whether y is a numeric value or a categorical value, the supervised learning techniques, supervised learning algorithms can be called as what are known as regression or function approximation problems. When the y is categorical variable, we will call it as what is known as classification. Now we are dealing with one such technique, supervised learning technique, which is the linear regression. So difference between classification and regression, we have already talked about. If y is categorical, then we have classification problems. If y is numerical, then we have what are known as regression problems or functional approximation problems. Regression, supervised and unsupervised. Regression is a supervised learning technique because y is numerical and y is given. The goal is when a new test data point xi is given, we wanted to predict yi hat. So this is the overall setup for the regression exercise. So these three questions that I have asked, I think all of you are comfortable, right? Type C in the chat box if you are comfortable and know the answers for these questions, because this is important. So all the summary is regression, linear regression is a supervised learning technique, which is a function approximation problem. Janik Raman, does that help? And going back, y hat, y cap is an estimate of y. That's the reason why I have used y cap. You will get it. You'll get adopted and see more of that sorts in the lecture. I have just given a flavor for this. Right. So this is a plan for the regression. We will introduce what is a regression. We will also introduce a notion of how does a linear regression model form look like. And when we say when we're building a linear regression model, ideally what are you doing is what the parameters, you are estimating parameters. What are the parameters that are there? How do you estimate them? What is a general approach to solve the linear regression problems or regression problems in general? We would illustrate that with an example with a problem statement. How do you formulate that as a linear regression problem? How to build a model, and then validation and also look at what kind of tests that are needed to be done. You'll get to know that, Subhash, in a while from now. So just to give a quick answer for that, this is the data, okay, that you have got. These are features. This part is clear, right? What are you trying to do is you are trying to get a model which is y is a function of x. X are features. Okay. Depending upon what function form you choose for this f of x. That means if you are choosing a function form of this sort, beta naught plus beta 1 x1 plus beta 2 x2 plus beta 3 x3, because I'm just writing three features here. What are parameters is these things, beta naught, beta 1, beta 3. They're all not same. Features and variables are same. Parameters are the parameters of the model that we are talking about. I hope that gives some insights on your question, Shivash and Saicharan. You have to correct your understanding. Of course, maybe you would have, yeah. So somebody would have talked about this as a parameters, but that's kind of not correct. We call them usually as regressors or what to say, features or independent variables like this. So these are the synonyms that are generally used when you are looking at a model. The parameters of the model are the parameters that we are talking about. What are beta naught and etc. Yes, that's all the linear regression is all about. We are going to cover that once in a while. Yes. Okay, this is a plan. So what is regression, by the way? So if you have attributes that are given like x1, x2, x3, and so on, x5, and because it's a supervised learning, you should also have y's. We have correct information, and what you are trying to do is, these are all independent variables or regressors that, as I was just talking about, and this is a dependent variable which is dependent on this attributes which are x1, x2, x2, and so on, x5, right? What is functional? So the goal is to obtain a function relationship between the dependent variable and the independent variable. Okay. So now the dependent variable is y, and we want to get a functional relationship between the dependent variable and the independent variables x. Okay. Sometimes nobody explicitly says this y is independent variable, y is dependent variable. You should be able to get from your physics or the domain knowledge that if these attributes are given, if this is a strength of a polymer, if these are the process parameters, then you should be able to choose based on your domain knowledge, this is a dependent variable and these are the independent variables. That is also possible. But most of the times for your exercises and so on, generally they will specify what is a dependent variable. Yes, you are correct. I don't know who asked this question. Y changes as the x changes. That's the reason why it is called as a dependent variable. Right. So if you have this notion, yes, that's all the linear regression is all about. You are trying to fix the function form as mx plus c form, and you are, how do you obtain these m and c values optimally? What is optimality that we are trying to get is, we will see. So we wanted to express these dependent variables as a function of independent variables, depending upon, that's all regression is. So if you are looking at general regression, what you are trying to do is we wanted to regress the dependent variables as a function of the regressors. That's the reason why it is called as a regression problem. So there was some question about the use cases for the regression problems. I think Mahalingam has asked about it. So in healthcare, the example is like insurance companies would like to understand the association between the healthcare cost and aging. That means basically, if your healthcare cost is y, you wanted to build a model as a function of x. X is attributes which are your age, height, blood pressure, like that, and you will fix the insurance premium based on this model that you got from all the previous data of your clients, and then decide on what insurance premium has to be given. What would be the insurance premium if the person has certain features like this? So X1, X2, X3. X1 can be age, X2 can be the BP, X3 can be heart rate, right? If you have built a model which is of this form, beta naught plus beta 1 X1 plus beta 2 X2, that is the outcome of final your predictive analytics. That's your model. When a new data point comes with X1, X2, X3 data, you will be able to find out what would be the insurance premium price that I should quote for him based on the data that has been given by the client. So what are you trying to do is build a predictive model based on regression using your, these are the parameters. If it's confusing, if you assume there is only one variable, mx plus c, m is a slope and c is an intercept. These are replacements for this m and c. I just used beta naught because I will be able to write this whole beta as later beta naught plus beta 1, beta 2, and so on as a matrix. That's only the notation. They are part of the model and they are the model parameters. Okay, I hope that answers your question. Right. So what are the other examples in engineering that I have just talked about, right? So if you are measuring a mechanical strength of a polymer from, you are able to, so you wanted to characterize this mechanical strength as your Y, and the attributes that you wanted to build a model from are the temperature, viscosity, and other process variables that we are measuring. This is, and if you want this function form to be a linear one, which is like beta naught plus beta 1 T1 plus beta 2 T2, such model is known as a linear regression model. And nobody says that you just wanted to build a linear model only. Depending upon how this actually affects, you could choose for a nonlinear model also. All the coefficients are slopes, one except one. This one is an intercept. The other ones are the slopes with respect to different dimensions. As the features increases, the dimensionality increases. Okay. In a two-dimensional plot, if you are having only 2 dimensions, this is y is equal to, okay, even if you have 1 dimension only, then you can write it here y. Let me just, yes, it's for a d dimension side. You're correct. So this is 1 dimension. I have only 1 attribute. I can only draw 1 axis here, and this is my output variable, which is y. Okay, y is equal to mx plus c is the equation of this line. Okay, if you have 2 attributes, I have to draw. So for 1 attribute, I can draw in a 2D. For 2 attributes, I need to use 3D. For 3 attributes, I have to go for 4D. And the regression line that I'm going to fix or fit in 1 dimension case, it's a line. In a two regressors case, it has to be a hyperplane of, okay. So how many regressors? So in a 3D plane, it would be a 2D hyperplane that is separating, that is actually fitting in a best projections. I'll show you a picture, you'll get a better understanding. So yes. So does it answer your question, Sai Charan? Yeah. So regression is one of the most popular supervised learning algorithm predictive analytics because it's a simple model. So there was a question from somebody, which model is best? So, the answer is from one theory which says that the simplest model that does the job with the minimum model parameters is the best. Okay, that could do the job with the minimal model parameters is the best thing to use. Okay, regression is a supervised learning technique. This we have already discussed because we need the knowledge of both the outcomes y and also the feature variables in the data which are x's. So this is the summary of this slide that is there. Dependent variables are denoted by y1, y2, y3, and so on. And so we are looking at a supervised learning framework because we need because of that we need a labeled data, right? So the thing I'm talking about is the following: we will have x1, x2, x3, y1, y2, y3. Okay. Each of this can be size of m by 1. That means how many samples are there? M samples. If m samples are there, each of these matrices would be, each of these vectors would be m by 1, m by 1, and m by 1. Okay. And the y's are generally called as response variables, regressants, predicted variables, output variables. And x's are m by 1s. They are called as a predicted variables, predictor variables, regressors, yes, explanatory. Sorry, this is explanatory, not exploratory. Explanatory variables, input variables, features. These are the several synonyms that can be used, and none of these synonyms has a notion of this parameters here. So that's the thing I was talking about with somebody when they have a confusion. I think so. Okay, so what are the different types of regression problems that are available? So when you're looking at the regression problems, we could classify them based on the function form that we wanted to choose. Ideally, we wanted to express the dependent variable as a function of the independent variables. Depending upon what function form you choose, that is the nature of relationship you wanted to build, you could classify them as a linear regression problems or nonlinear regression problems. If you choose a linear function for this, then it falls under the linear regression problems. If you choose a nonlinear function, then it falls under the nonlinear function. Okay. And depending upon the number of dependent and independent variable problems, variables, that we can classify some regression problems like this. If you have only one independent variable and one dependent variable, such problems are known as univariate regression problems. If you have multiple independent and multiple dependent problems, like what I have just talked about, the health thing, right? Y is equal to, we are looking at a linear multivariate means basically we have more than, so beta naught, beta 1 of age plus beta 2 of weight. So how many regressors are there? How many independent variables are there? More than 2, more than 1, right? So such problems are known as multivariate. Maybe this is an insurance price, or you are looking at some other output also y2, which is also a function of this. Okay. Then such problems are known as multivariate regression problems. If you have more than one independent variable and more than one dependent variable, then such problems are known as multivariate problems. Now we are looking at a simple case where there is only one independent variable and one dependent variable, and we are choosing a model form, which is a linear form. That is y is equal to that will be one dependent and multi-independent variable. What would be an example for more than one dependent variable? Yes, so basically you could think about something of this sort. So we have the variables x1, x2, x3. Okay, these are your regressors. Your output variables are y1 and y2. So imagine a situation where these are your output variables, right? So I'm just thinking about an example which has, yes. Let's say these are some engine parameters, right? Engine age. Yeah, I'm trying to get that. Let's say this is an engine age. This is engine number of kilometers run. Okay. Let's say two examples. Let's not have this. Okay. So engine age and engine number of kilometers that the bike or car has run. Okay. What would be the mileage that you wanted to predict? That might be one of the, now the current, based on these things, you will wanted to assess what is the mileage that is one output variable, and based on these two features only, you wanted to predict the price of the car also. You see that? So that could be two output variables you might be interested in. That would be evident from your problem statement itself. Okay. So what I'm trying to say is there might be a possibility that there might be two or more independent variables or one or more independent variables, so dependent variables also. I hope that should throw some light on what type of problem Janik Raman and Himanshu. You see that, right? This is what I was talking about the other time. So this is how many attributes are there? Two attributes, and you have one dimension for your output variable. So earlier case, I was just drawing X and Y. I have only one attribute, and if I wanted to fit this is my data, and if I wanted to fit a linear regression line for this, what I would do is I'll try to find. The whole exercise is to find out this linear equation which will fit the data well. Okay, I am trying to get this model beta hat y naught is equal to beta naught plus beta 1 plus x1. So the regression problem that is for classification. Subhash. Logistic regression is a classification. Of course, that's a linear boundary that separates the classes. That's a linear classification model. Okay, that's not a regression problem. You are not able to predict what is a y value. The y is a categorical there. That's the difference between the logistic regression and the linear regression. Okay, so this is a linear model which are having two attributes. So for one attribute, I need a 2D plot to plot. For two attributes, I need a 3D plot to plot see the regression. Okay. If it is a nonlinear regression problem, that is how the overall nonlinear model would be looking like. These are just pictures that I have taken from Essentials of Statistical Learning from Tipshuran. Just to give a visual feel for this. Subhash, I hope that your question is answered, right? The logistic regression is a classification algorithm. It doesn't have something to do with the linear regression. Right? Everybody followed the basic idea of regression, right? So we wanted to build a model which is of y is equal to f of x. Depending upon what model form you choose, you will be dealing with a linear regression problem or nonlinear regression problem. And we have also segregated this regression problems based on how many attributes are there, how many output variables are there. Okay. So what you are going to cover in this part of the session is like we are looking at the univariate linear regression. That means you will have only one x and you'll have only one y. And you also fix the function form. So then you are looking at y is equal to f of x. You also fix the function form to be linear, which is y is equal to mx plus c kind of thing, where here we have m as beta naught and c as beta 1. If people are there, just get confused between these betas, you can just have this picture in the mind so that you'll follow the rest of the things. Okay, what is the goal now? Given this data like x, y, x1, y1, x2, y2, x3, y3, x4, y4, let's say x100, y100. The goal in the simpler linear regression is you will do all the necessary steps that you do for building a machine learning model. You will do scaling, all these things if you need it. And also you will do the train and test data separation, right? And you will now take a training data to extract the model. So that's I think that's where we are starting. So when you say I'm trying to build a machine learning model, a linear regression model, the whole goal is you have fixed this form, which is beta naught plus beta 1 x, and that relationship has to be satisfied for all the data points that are there. Okay, if your model is y1 hat is equal to beta naught plus beta 1, you can have individual betas also. Would say beta naught 1, beta 1 1, okay, plus x1 times x1. This is your estimated value of y. So what is the true value of y? You know that because it is true value of y1, you know that because it's a supervised learning. There will be an error in y hat, of course, but there won't be error in y hat per se. When I say y is this much, then I will have to add it. Y hat is this much. Okay. So when I'm saying the error, that what would be y1 minus y1 hat, that would be this epsilon I. For every data point I, this is going to be epsilon. This is epsilon I. Because if this model is not able to capture all the information that is there in the data, then there would be some residuals. That residuals are important for us to track and understand whether a linear regression model is sufficient for the data or something else has to be, or should we actually go for a nonlinear regression model? I'm sure. Okay. Everybody following? Are we on same plate? Type F in the chat box if you're following. Yeah, I can see only 3 Fs. That means the others are already in the sleeping mode or what? Service. Okay, so thanks. Yeah. Thank you. Right. So this is a problem that we are looking at. The error is now yi minus the estimate of yi, which is beta naught plus beta 1 x1. Okay. So now you can see that for every data point, there is going to be some error. And how are these errors distributed? Are these errors having any other information from the model that is not being predicted? Are the metrics that we use to test whether the linear regression is done properly or not? This we will talk about as we go along. But when you are saying, when you are building a linear regression model, what you are trying to do is to predict or estimate these beta naught and beta 1. That's where the whole linear regression problem boils down to. If that is followed, now we have to formulate this as an optimization problem. And then, so what is an optimal value? The geometric view of this is the following. So if you are looking at x as your attribute and y is your thing, this is x1, y1, this is x2, y2, this is x3, y3, x4, y4, x5, y6, x6, x6, y6, x7, y7, and so on. What I am trying to do is I am trying to build a model without loss of centrality. I can draw this from the origin itself, because if my beta naught is 0, then it will pass through origin. If my beta naught is not 0, then it has some intercept. Okay. Okay. So now what I'm trying to see is I wanted to build a line. We wanted to find out this line equation, which is y is equal to beta naught plus beta 1 x1 or beta 1 x. My goal is to find out this beta naught and beta 1 from the data points. So how do I find out? What is the thing that I'm trying to find out? I'm trying to find out this line. When beta naught and beta 1 changes, this line changes, right? Among all such lines, I can draw one line like this. Let me take another color. I can draw another line like this. Sorry, very bad at drawing this. So I can draw another line, let's say like this. I can draw another line, let's say like this. I can draw another line like this. So which of them is a better one? All of them are linear lines, right? What is the objective that I should solve? The objective that I'm going to formulate is, we know the error from each data point is this epsilon I, which is given by yi minus yi hat. Okay. That error is, yes, that error is, I am going to put this function, which is known as sum squares of errors, as my objective function. So when you are looking at an optimization problem net framework, I would like to minimize the sum squares error from each data point, and I will find out this beta 1 and beta 1, beta naught and beta 1 such that the sum square error is minimized, is what is going to be my optimization problem that I'm going to solve. I'm not sure whether all of you have followed it, because if you have not studied optimization at all, then this might be looking daunting to you. So the idea is this one. Let me draw this picture a little bit more carefully so that you will get a geometric feeling of this. So the point I want you to understand is there are several different lines that are possible. Which line is the best line to take, right? So how do you decide it? I will have these distances from each of this point. So this is, let's say x3, y3. This is, let's say x4, y4. Okay. This is the true value of y3, right? And this is the projected value of that y3 onto this line. Okay. That is what is being predicted by the model. If this line is chosen, that is what is going to call as y3 hat. The difference between this thing is y3 minus y3 hat. This is for one data point. I'm going to square it, and I'm going to do it for all the data points that I'm going to look at. So that's what is known as the sum squares error. So y2 minus y2 hat square plus y1 minus y1 hat square. So because it's a square of errors and the sum of them, then it is called as sum squares error. I am going to choose these parameters beta and beta naught and beta 1 such a way that the sum square error of all the data points is minimized, is what the problem that we are going to solve. Is that clear? At least a notion of what is an objective function when you are trying to build a linear regression model. Okay, good. So there are certain assumptions that have been taken when we wanted to build this linear regression model, which you have to verify at the end. I'm just going to state these assumptions, okay, such that we will verify it at the end of, after building a model. If all the information in the X's are captured by this model, then there shouldn't be any information in the X and epsilon. Information in the epsilon that is related in the X. So what you are trying to say is, this is your yi hat, which is beta naught plus beta 1 xi hat, xi. Okay. If this is a perfect value, then there shouldn't be any information that is left out in the xi that is in the data that is available in the epsilon I. So xi and epsilon i's are uncorrelated. This is one of the assumptions. Once when you're taking this model like this, and when you build it, and we are going to use it as a model like yi is equal to beta naught plus beta 1, what it should satisfy is this property that xi's and epsilon i's are uncorrelated. That means there is no information left out in the errors or the residuals, which is not being captured by the model. If there is some correlation, then that means basically some of the information is not able to model by the linear form. Okay, and the epsilon i's are uncorrelated with each other. That means there shouldn't be any pattern in the epsilons also. It should be a kind of white noise thing. So what is that? For every data point, we have epsilon 1, epsilon 2, epsilon 3, right? It is like a random variable. We don't know what value it takes it. All we wanted to say is when we plot this, the epsilons with respect to X, they should be uncorrelated, and the covariances or the correlations between these things should also, there shouldn't be any correlations between the epsilons themselves. That is the second assumption. And these epsilons follow a normal distribution with a mean 0 and some variance epsilon I. And this epsilon I is also should be constant for all x's. That is another assumption that we are trying to say. So if you are plotting the residuals, what you wanted to see is a flat line. There shouldn't be any trends between the xi's and epsilon. That is also tells about this point, which is xi's and epsilons are uncorrelated. If there is some trend between the epsilons and independent variables x, then what we call them as a heteroscedasticity. But for the linear model to be correct, there should be a homoscedasticity should be satisfied. If you don't understand all of this, just bear with me. We will check all of this once we build the model also. But these are all the assumptions that has gone in building this linear model. When you assume that the linear model is correct, these are the things that has to happen. Okay, this is called as heteroscedasticity. If all these things are satisfactorily verified, then we can say that your model y is equal to mx plus c or y is equal to beta naught plus beta 1 x is correct. So now there has to be some ways of verifying these assumptions, which are known as diagnostic plots for the regression problems that we will look. The point is, once you just build a model, it is not over at that point. You have to do all these diagnostic things and verify whether the assumptions that you have made on these things is being validated or not, is what you have to keep in mind. Okay, so let us well into the next aspects of the problem. Okay, now as you have already seen, the whole problem of building a model, a linear regression model, has boiled down to the estimation of these parameters beta naught and beta 1. Okay, we have a model y is equal to beta naught plus beta 1 x. Okay, so how do you estimate these parameters? We have seen that the error is yi minus beta naught minus beta 1 xi. When you square that up, that is the error square. This is for every data point. Okay, and when you sum them up across all the data points, what you get is known as the sum squares error. That is what is known as the sum squares error. You follow this equation. That's exactly what I have tried to written there in the previous slide by using a graph. Type F in the chat box that if you have followed this expression, the sum squares error expression. Great. Now, I'm not going to derive how this beta 1 hat and beta naught hat are these expressions. All I will just show is this thing. So when you solve an optimization problem, which minimizes this, minimize sum square error, and find out beta naught and beta 1, when you solve this optimization problem, what you get is beta 1 is the SXY divided by SXX. That means the covariance and the autocovariance of the x's. So if you are not happy with this, just live with this ones. So essentially the beta 1 can be estimated from the data itself like this. So if we have xy, I think most of us would have done this exercise in at least 11th or 12th. So what you do is, for all x, you will find out the mean, that is your x bar. For all y's, you will find out the y, that is your y bar. And you have I is equal to 1 to n data points. Okay. From every data point, you can do that. Subtract that xi minus x bar. That would be your this xi minus x bar. For all other data points, for y also, you can do that yi minus y bar. Okay. So when you sum this up, that you will get a sigma. So then you will do a product of this and then sum it up across the product. You will also do this x minus xi whole square. Sum that up. When you divide them in a simple Excel sheet, you will be able to get an estimate of beta 1 hat. Okay. You know the y bar from here, and you know the beta 1 hat from here, and you can get the x bar from here. You will be able to estimate the beta naught hat. So this whole exercise can be done in a Excel sheet from the data itself. So nevertheless, when you implement this algorithm in the Python, what it will give is the estimates of beta naught and beta, directly without you doing any of these calculations by solving an optimization problem inside it. Okay. Now followed beta 1 and beta 1 hat are same, right? There is a little bit of difference between them. You see that when you are just writing the final model, you wanted this beta to be a scalar quantity. Okay. But this beta is not a scalar quantity because for every data point, we are having one beta naught and beta 1 value for every data. So what you are trying to do is this will have some distribution and with some mean. That mean value you will use it as beta naught, beta 1 hat and beta naught hat. Rahul, you following? Yeah. So there are the estimates of this beta. So whenever there is a hat, you should understand that they are the estimates of that particular parameter. Similarly, that's the reason why I have written YI hat. Why YI hat? YI hat is an estimate of YI. If you ask me a question, if YI and YI hat are same, that is same when your errors are 0. So when you have no errors in X and no errors in Y, then we call this procedure as what is known as ordinary least squares. This is what is known as the simple linear regression ordinary least squares because you have only one attribute and one output. So general procedure for regression is as follows. Okay. So we will start with the formulation of the problem. That means you have to know what is your Y and what is your X here. Okay. Choose a set of form of the model, method for fitting and specific assumptions that we are following for that method. This is general for all the data science models, but I'm just talking about in terms of regression. Okay. So use the method of fitting and then fit the model, validate the assumptions. What are the assumptions? Are X's uncorrelated with epsilons? Are epsilons, are there any outliers if you're in the model and you do the sensitivity analysis, all these things. So if all the assumptions are validated, then you can evaluate the model on the test data. So if the test data results are satisfactory, then you will take this model as the final model and use it for the intended purpose. If the assumptions are not valid, then maybe you have to go back and change the form of the model, right? So if the fitted model is not okay, then also you will go back and do this. So what I want you to observe from this is, it is not a simple one-step process. It is an iterative process where you will build the model, validate, so check for the assumptions, whether all assumptions are satisfied or not. Unless you satisfy all these assumptions and have a model, you should not go for the test data. Once the test data is there, so basically the error must be very low. That is at that peculiar point, we will get optimal M and C, not X size error. Okay, so this is general procedure. So this is an example problem that we would like to use to illustrate this linear regression. So this is the data that we have. We have one, this is your X, this is your Y. And the reason why I have just put the units as X and minutes as Y is because the more confident values we have, we wanted to have that as X. Because this, so let us just define the problem statement first. So there is a serviceman who take the service calls and work on it. Okay, the service agent, and these are the number of units that he has repaired across 14 days in a month. Okay, so and day 2 he has repaired some 2 units. Okay, and the time that he has spent on it is, let's say, 40 minutes. Okay. Objective like that, he has worked for 14 days. There are 14 data points, and the time that he has spent for repairing that many units is given here. Okay. So the objective is to find out the relationship between these variables. So you wanted to say, like, you wanted to know, ask this question: are there any model that I could learn? So let's say somebody asked me later that how much time is needed for to repair 9 minutes, so 9 units. Then if I have this model, I will be able to predict this is the time that is needed approximately for this. So this is an example that we are trying to. So why is this taken as X and why as minutes? Why can't it be the other way around? So usually when you are doing this data, that actually boils down to the point. Like sometimes I told you that sometimes nobody gives you what is your why. You have to use it from your domain knowledge that what would be your why. Okay. So here, the number of units are accurate generally because it cannot be 0.5 and so on. There is a very less chance that there will be errors in this thing. But minutes, it might include a time he traveled and so on. This would be a little bit, skeptical to think about it as X. So the idea is the following. So the data that we are more confident, and also according to the physics, which could be X, we choose that one as X. And the data which is not very confident, and not very confident in the sense it has little bit, chance of having wrong values, you generally choose it as 1. Yeah, how much time we would need to finish? Ajay, I'm not very sure. We are actually running late. So I'll quickly go over this thing so that we can then later. So this is a problem that we are going to take. If you take this YA, the idea is here to estimate the points, right? So there are all these units and minutes. And let's say I have fitted this line, which is YA hat is equal to beta naught plus beta 1 hat xi. And the error between this model predicted value and this one is your EA, epsilon I. Okay. YI is this model. Because, so when I write YI here, if the model has predicted everything, then this epsilon I would be 0. Because there might be something that is not predicted. To accommodate that, for that, I will write this epsilon I. And why is it? So somehow if the problem is solved by linear regression or non-linear regression. Yes, you will know from the diagnostic plots that we are going to talk about. We will start with the linear regression because it's a simple thing to do. If you are not able to find out from the called as diagnostic plots, you'll be able to find out. So the other way is you would, when you're visualizing, if your attributes are low, you will be able to see some trend in this thing. I'll show you one example at the end so that you will be able to get a feel for it. So first thing is, if you could visualize the data, if that has some nonlinear trends, then you should try that. It will give you a notion that some kind of nonlinear regression is needed. If you're not able to visualize, fit a linear model from the diagnostic plots, you will be able to get whether you wanted to use a nonlinear model. That example I'll show you. Sorry, Charan. Yeah. So this epsilon I is now defined as yi minus beta naught minus beta 1 xi. This is a sum squares error, and this is the thing that I have already shown you. When you implement that in the, you just need to call this. You have to. Yes, that's what usually the curve fitting solves an optimization problem, and that is a regression problem that I have already indicated, right? The problem is the more and more parameters that you have in the, that leads to overfitting. So you see better accuracy for the training data, but for the test data, if you use it, it will predict work poorly on this thing. Overfitting is a problem when you are looking at a nonlinear models with a high number of parameters. So, okay. So this is, so when you run this case, for you to implement, all you need to do is to give the training data of X and Y to the linear regression model in the Python. Then you will get this beta naught and beta 1. So now we are talking about assessing the model. Like, is the model correct? That's where we wanted to think about some metrics of this, right? Why use minimization of SSC? Good thing. So what else you can use? You can use some other objective also. I would say I would not square. I'll just use the modulus of this thing, YA minus YA hat. That is your choice. Generally, this is used. That has some connection with this, the assumptions also. Okay. These are, so when you have such kind of thing in square, that basically represents some circles. That's the reason why, if this is your error, right? This errors, if they are uncorrelated, and then, so I don't know, I'll be able to explain all of this to you, or you'll be able to grasp it. So essentially, they want these epsilons to be from a normal distribution. When you have a normal distribution with the same variance, all the epsilons that you have would be having same variance. So normal distribution variance can be represented by an ellipse. If all of them have that, the circular thing would be all the variances are same, then we'll have a circular kind of thing for the variance of the random variable. Okay, so there are reasons that I cannot explain now because of the time constraint. So the general notion is you can go for this this one, which would complicate the optimization problem solution, because the squared functions are easy to solve the optimization problems. You could use any other objective function to minimize, to get the beta naught and beta 1 values. That is all there. So this is one of the forms that you could use. Okay, Pankaj, I hope that answers your question. At least some notion you could check on it. I mean, there are reasons that has connections with the assumptions that we have taken for the residuals. The normality assumption comes from that. If you choose, can we also compare with the average line? How much better results were? What is average line? I didn't get it. What do you mean by average line? Okay, so think about it. I didn't get your question. What do you mean by average line? Okay, so the question now is taking simple average of unit per time. That would be only 1 point. Where is the line? So what would be the value you will say? For 100 units also, you'll say the same thing. I didn't understand this. What do you mean we can withdraw that for each unit? So the goal is, when you have a linear model like this, y hat is equal to y hat is equal to beta naught plus beta 1 x. Then whenever you give a x, I will be able to predict this. So I'm not sure, Surya, because several faculty teaches. Okay. So that's all. When you finish the linear regression, we will leave. There is no next topic. Surya, let us go into this. Okay, so we would have already talked about, seen this linear regression metric, which is R squared value, which is also known as a coefficient of determination. So R squared value you would have seen. You would have other notion of what is known as adjusted R square. To when you are fitting a line in Excel, you will see R squared value. Usually R squared is equal to 1 is a good fit. And if you think that R squared is only the metric, then it's a problem. I'll show you counter examples where even R square value is good, but the final model is not good because it is not satisfying some assumptions that we have taken. The other question we should ask is beta naught plus beta 1. It will give you an estimates of this coefficients, but it will also give you the confidence intervals for these things. Whether this parameter is significant or not is the question that we would ask. That's where this hypothesis testing would come into picture. Okay. The other question that we would like to answer is, can we improve the quality of the linear model so that we would be able to see whether all the assumptions are matching or not, all the assumptions satisfying or not. If they are not satisfying, then maybe you will get a notion that the linear model is not good thing. You have to go for the nonlinear models. So we will also look at the outliers. How are they influencing the model? So what is normality of errors? Basically, we want the epsilon i's of all the data points should follow a normal distribution of zero mean and sigma square variance. Homoscedasticity means errors in different samples have same variance. Uncorrelated x and y's, x's and epsilon i's. This is what I was talking about. If all the information was captured in the model, then there should not be any relationship between the residues and the x's. Okay, these are the model parameters that we would like to see that. So R square is the first thing that we do. Hypothesis testing for asking a question whether beta naught and beta 1 are significant, or I can just live with this beta naught or beta 1 only. If it is only beta naught, then there is no line. That's just a straight line. That's just a intercept line like this. Unless there is a slope, then there is, this is how it is. So if beta naught is not significant, then we will get a line passing through the origin. If beta 1 is not significant, then there is a horizontal line like this. So that's what we wanted to test. We wanted to do outlier analysis, and this one analysis of variance we don't do. We generally do it for multiple linear regression only. That we are not going to talk in this lecture. Okay. So what is R squared? How is it defined? Is given here. R squared is 1 minus ya hat whole square divided by ya minus y bar whole square. So what does this term on the top represents? It represents the variability explained by this model that we have chosen, which is ya hat is equal to beta naught plus beta 1. Whatever is the total variability in the data that is given by this particular ya minus ya. So this was the question that probably you are asking. You just look at the means and time per unit. What you are trying to do in the R squared is you are looking at around that mean, what is the variability that is there. That's the total variability in this. This is kind of a term on your variance, right? So this is a variance. This is a variance explained by this model. This is the variance in the total data. So R squared close to 1 is a good fit, but R squared should not be used as a sole criteria for this thing. Okay. I was talking about, there was a question whether beta 1 and beta 1 hat are same. They are not same. Beta 1 follows a normal distribution because there are several values that will have a distribution which is a normal distribution with a mean beta 1, that is an expected value of beta 1 and the variance sigma square by sxx. So this is the difference between the beta 1 and beta 1 hat. Somebody have asked, right? I just wanted to. So what is this expectation of beta naught hat is beta naught? That means there are several beta naught values and the most, that's the average of that thing, expected most possible values of this beta naught is your beta naught. Beta naught hat is your beta naught. Similarly, the expectation of beta 1 hat is your beta 1. Okay. So that is the answer for this. So when your model is given, when your model form is given, let's say premium is equal to 4.5 times the age plus 2.5 times the height. Okay, I'm just looking at only one example, right? Okay, 4.5 times the age plus some constant. It's a 5. what your algorithm also gives is the confidence interval for these parameters. This is your beta naught, this is your beta 1. This confidence interval has been given to you based on the variance of this beta naught and beta 1. For beta naught, for beta 1, this is the values. So you don't need to really worry about these expressions and by heart them. The SB1 you can calculate from the data directly like this. All of this data will be given to you by the model. So the point that you wanted to remember is, if this confidence intervals covers 0, that means, let's say the confidence interval for the beta is something like this, minus 2.0 to 2. Then what happened is the 0 is in between the confidence interval. Then you say that this beta 1 is insignificant. If the confidence interval covers 0, then we say that that particular parameter is insignificant. Similarly, the confidence interval, you can look at the confidence interval for beta naught, and if this confidence interval covers 0, then we say that that particular coefficient is significant. These confidence intervals will help us to make a decision that whether a particular parameter is significant or not. That can be actually tested by using what is known as the hypothesis testing. In the hypothesis testing, what we have is generally null hypothesis. That means what you think is true. Alternate hypothesis is an opposite of this. So I am trying to test whether in this model yi hat is equal to beta naught hat plus beta 1 x. Okay. My question is, I am speculating that beta 1 is 0. That means it is not significant. The alternate hypothesis is beta 1 is not 0. Okay. If this is true, the reduced model would be beta naught plus epsilon 1 because beta 1 is 0. The alternate hypothesis says that no, the full model has to be considered. Okay. So when will you reject your null hypothesis? Is if you reject your null hypothesis if the confidence interval of beta 1 includes 0. Similarly, the confidence intervals of beta naught includes 0, then intercept term is insignificant. So this is the discussion I was talking about. So we were talking about this R squared, right? When you get a linear equation from the data, is the job done? No, it is not. We have to verify assumptions also. So let's say this is a data. You see that but these are different data sets that are there, x1, y1, x2, y2, x3, y3, and we have fitted a linear model for all of them. So these are the intercepts and the x1 values. So this is beta naught, this is beta 1, and this is beta. Okay, the model is y1 is equal to beta naught plus beta 1 x1. So if you see that for all these things, we have a same line. For this line, for this data also, we have this equation, which is 3.5. For this kind of data also, we have a linear model that has been fitted, which is having a beta naught and beta having the same value. Similarly, this one also, we have this 3 and 0. And you can really see that the linear regression is good for this particular data, but not all of this. Why? Because there is an outlier which has pulled this line this, and there is this whole data itself is some kind of problem because you have got all the x's, you have got the y values at all the different x's, same x, but you have different y values. So the point is, just when you build the model, it is job is not done. You have to validate. You have to do analysis for fitting if the model that is fitted is good or not. So what are those analyses? The first questions you should ask is whether the all underlying assumptions are satisfied. Are there any outliers? Are there? Basically, if you have removed outliers earlier, then we don't need to ask this question. Okay. Does some observations influence the model more than some others? Can the regression equation can be improved by nonlinear model? So that these are the questions that we should be able to answer from the model diagnostics. Okay. So let us dwell each of them in a detail now. Okay, so how do you answer them? The question is, we wanted to plot this residual plots. So what are the residuals now? We know the epsilon r EI is yi minus yi hat. We can formulate the variance and the covariance of all the errors using this particular formula. Okay, don't worry about the mathematical details of this. You will be able to calculate them just by using some function, variance and covariance in the plots. So if epsilon I, what is an assumption that we made? Epsilon I has to be a normal distribution with a mean 0 and the variance sigma square. We can define what are known as standardized residuals, which are given by Zi by dividing that with the variance of that, and the PIA has already given. When you there is a function to standardize that also. So we can calculate the standardized residuals, which is a normal distribution with a 0 mean and variance 1. Once that is there, we have to check the residual plots for the standardized residuals for the validity of the linear model. That means Xi's and epsilon i's should be uncorrelated. That is this thing. Normality of the residuals that you could check with the QQ plot. Homoscedasticity and heteroscedasticity vectors you could plot with respect to yi hat and epsilons. And then if you see any trend, then you don't have a homoscedasticity. If you have a flat line kind of trend, that means the data are equally distributed, then we'll say that this homoscedasticity assumption is satisfied. And when you plot y hat versus the epsilons, they should not be correlated. So I'll show you the plots. Okay. So this is, you can plot with respect to y hat or the at x also, which is your regressor. What is it trying to say is all the residuals are distributed in a fashion that there is no trend in this when we plot the data with x and this thing. That means for the data set 1 that I have shown you, the linear model is good. In the data set 2, you are seeing a kind of pattern here like this. What does that mean? Basically, there is some amount of data, some amount of information that has not been captured in the model and that is still there in this. So let's just look at the data like this here. This is the data and you are trying to fit a linear model, right? What happened is whatever has been modeled by a linear model has been there in this equation, line equation. Whatever is left out is actually being visible as a pattern here. So this will give us a thought that no, a linear regression model will not be able to fit this kind of data and I have to move for a nonlinear regression. So this was a question that Sai Charan or somebody have asked. If you have plotted the data before and see some nonlinear trends, then you would better go for the nonlinear thing. If you have not known because of you cannot plotting the data, visualization is difficult, then once you fit the model and then look at the residual plots, you will be able to find out such patterns in the data, indicating that the linear regression model is not good. You have to go for a nonlinear model. If you see that there is some trend here and there is one data point that is there, that means basically this was being influenced, this model has been influenced and there is some trend that is not being captured in the model. Shape of the pattern is based on the information of the function that is still available in the residuals. This is what we were talking about. Xi's and epsilon i's should be uncorrelated. There is some correlation, such kinds of patterns you will be able to see in the residual plots. So how do you test the normality of residuals? You would use what is known as a QQ plot, which are called as a on-time plots. There are functions available in the R and Python to plot them. Okay, you just use the standardized residuals and it will try to generate a plot something of this sort. Normal QQ plot. These are the theoretical quantiles and these are your quantiles calculated from your residuals. If all of the data points fall into the 45, like that means your assumption of this epsilon i's should follow a normal distribution of zero. The standard residual ZIs should follow a normal distribution and unit variance is valid. If not, then there is some problem with the assumption that you have made. You have to go back and then look at these things. What is this homoscedasticity and heteroscedasticity? When you plot either y hat or x, usually we will plot y hat in the x-axis and the standardized residuals in the y-axis. They should be distributed like this, and there shouldn't be any patterns. Okay, and the values of all the data residuals should be within one limit, which is 2 and minus 2 in some cases, and 4 and minus 4 in the cases. I will tell you when to use what case. And when such things are there and there is no particular trend that is being observed, then your homoscedasticity assumption is valid. All these plots you could draw from the variances that you have. So from the epsilon i's that you can get from the model when you implemented this Python. Maybe in the hands-on, they will show you this. I'll also give you a link which talks about the Python implementation of similar example. You'll be able to better appreciate that. Okay. So what are this standard? So if you have some kind of funneling like this or some kinds of trends in this standardized residuals, this is what is known as heteroscedasticity. So if you found out something of this sort, then you will say that, look, my linear model is not going to help. You have to go for non-linear model. So other important thing that affects the linear models is outliers. In the third example, there was one point that is far away and it is trying to pull that line far from this thing, right? So when you plot the standardized residuals, if there are points which falls under the -2 and 2, then we call them as outliers for the data points for the class, for the data of small and moderate size. And for large data sets, the standardized residuals after fitting the model should fall under this -4 and 4. Basically, from the data points that you have used for modeling, you are seeing, are there any standardized residuals that are falling out of this range? If there are, then you will say that there are outliers and you have to remove the outliers one by one and see whether there is a performance improvement in the model. So let us consider this example here. We have X as coupon rates and the bid price as Y here, and this is the data. You can clearly see that these data points are off from this thing, and there are some data points are off from this. So when you estimate a model like this, you will have beta 1 and beta 1 have values, and the standard errors, the t values that I was talking about, which is a t distribution, and the confidence intervals also will be given. Okay, so R squared value, you observe it, it is 4.175. Okay, multiple R squared is 0.7516. So just remember, the lesser the p value is, the better the model is. So that is what you have to remember. Okay, now when you do the standardized residuals plot with this thing, you see that these are the data points. It indicates that they are outliers because it is outside the 2 and 2 range. Now what you have to do is, ideally, you have to take this data point, remove the data point, and then rebuild the model and see whether there is a performance improvement. Again, take this point later and do sequentially by removing one by one data point, and then you will see the increment in the model. So for now, what I have done is I have removed all these 3 data points and then built the model. Okay, this is the model without those points, and you can see that the R squared value is 0.84 now, as opposed to the 0.75 earlier, and the adjusted R square is 0.9891 as opposed to the previous value of 0.7441. You see that the outliers have influenced it. The procedure to remove the outliers and then improve the model performance is, look at the standardized residual plots, remove the outliers one by one, and then improve the performance of the model. Okay, so in order to summarize the steps that are there in building a regression model: collect, extract data, reprocess the data, divide the training data into training and validation sets, perform descriptive analytics or data exploration. Okay, and then build the model, do the model diagnostics, validate the model and measure the accuracy, and you can later decide on the deployment and you can use it for this thing. So collection, pre-processing, we have already talked about. If there are any missing data, we have to use data imputation. You can talk about you can know the outliers. All these things are part of the exploratory data analysis. If you need some feature engineering, we have to do that. So for example, if you have feature X1 and we see that finally in the residual plots that some kind of trend is shown like this, maybe I would then feature engineer this particular feature into X1 square. Then I will find out and I'll build a regression model for Y and X1 square. I'll call it as X2, but it is a squared variable of X1. This is what is known as a feature engineering, modification of variables that we would do. So this you would have already seen in your class 12th or something, where you can actually fit a linear model for a nonlinear data by using some transformations, right? So if you have y is equal to x square, if you take log y, then you'll have 2 log x. Then what I have done is basically I have transferred my variable here, and then so in this case it was not possible because you still have y is equal to e power log x. You see that some functions you will be able to transform and build a linear models for the nonlinear data also. So this is what is known as a feature engineering, and you can also do transformations. So dividing the data into training and test data, this is a very good thing. You need it. And the sampling for classification, you have to do it carefully. For this thing, it is fine. So training data is used for building models. Test data is used for validating them. And validation, there are several techniques: cross validation, leave one out analysis. This we are, some algorithms when we are discussing, we will talk about this cross validation. Okay. So these are the thoughts on the descriptive analysis. We can use box plots to find out the outliers, scatter plots to reveal the relationships that will tell us whether to go for a linear model or non-linear model. All these things, if you could plot and see, they're well and good. If you're not able to plot, then we have to go build a model and then look at the diagnostic plots and then comment about what kind of model that is going to be this. So we are almost done. So how can we divide the train and test data set? There are functions that are there that are available in the Python. Test, train, data split. You could, maybe you'll learn them if you haven't learned till now in the tutorial sessions that are meant to be followed. I'll also share you a link where they have talked about those things. Okay. Yeah. So then the next step is building model. Once you build the model, that's not the end. We have to do the diagnostics. The residual plots are the best ones to think about when we wanted to validate the assumptions, and the QQ plot. The other thing is overfitting. If you go for large number of parameters, in this case, linear regression, there is no large number of parameters, only 2 parameters. But when you generally, you can get it from IAB website also, sites and so don't worry. Okay. So overfitting has to be avoided. How do you do that? It's basically using some, so in the objective function, we are trying to minimize this, right? Minimize sum square error. For that, you will add another term for regularization. That means basically when you are adding new parameter, it should be justified on improvement of the modeling. If the model improvement, the performance is not improving and you are adding a parameter, it will penalize the objective function. Okay. So final step is to deploy the model, development strategy, and then you use it on this. So I'll just quickly go through this link here so that you will be able to understand the things that we have talked about in a better way. So I think we're all there, we're done. So just I'll want to show you and talk about like 2 to 3 minutes and what we have discussed here in that particular. So you see this. This is to predict the mileage using the horsepower. You see that this is the data. From the visualization itself, you can see that there is some kind of exponential decay in this, but there is a decreasing trend. If you want to just fit a linear model, this is how it looks. Obviously, this data has been chosen to show the intricacies and how this residual plots helps in them. So when you just fit a linear model, what happens is, so this is the basics of linear model that we are talking about. When you fit a linear model, what happens is when you have a residual plot with the y hat and the residuals, you see that there is a trend that is missing. This is obviously saying that your linear model is not able to capture this trend, and still there is some part of information that is left out. So I was talking about this thing. This is assumption of the linearity. Linearity, that means basically a linear model is not able to solve this. This assumption is failed. You have to look for this. Okay. Endogeneity, that is basically the relationship between the x's and the epsilon. You could check any one of them. You can see that if the epsilons are having some correlation between the xi's, then that should be evident in the residual plots. If you have some trends like this, that basically means there is a violation of the assumptions on linearity. The normality, this is a QQ plot. You see that there are some points that are missing out on it. Okay. And the homoscedasticity I was talking about, there is some trend. Ideally, it has to be distributed across all the y's without having any trend here. Okay. This, you see the standardized residuals that I was talking about. Okay, and all of this have a code that you could go through. Outliers, we have already talked about this, -2 to 2 and so on. You see that -2 to, so -2, these are all the outliers. What you have to do is you have to remove these data points one by one and then try and improve the performance. Okay. So how do you resolve this? Basically, they have used, you see this? This is your y, MPG is your y. This is the nonlinear model. Now they are trying to fit. They, instead of using the horsepower only, horsepower square is also being used. So what they're trying to do is the following. So they have incorporated the nonlinear thing here because they know that now the nonlinear is needed. So this is the residual plot for the nonlinear model, the black dotted ones, and this is the residual plot for the linear model. So this is how a residual plot should look like when you are having a good model for a regression. Okay, that is, and all of this is summarized here. You see this. This is a normality test. You see this normality test. This is heteroscedastic, homoscedastic, this is a test, and these two tests are for the validation of the model, linear model and non-linear model. See that final model. This is the initial proposed model, beta naught plus beta 1 horsepower. The final model is this one, non-linear model that has been fitted. You see that this article helps you in understanding the diagnostic plots of linear regression models. And all of this has dealt with only one variable. When you have two or more variables, the correlation between the variables and all of this come into picture. That would actually complicate the things. So Charan, you will get them when you get the slides, don't worry. Or you could just find out linear regression or take a picture and you can take it from there. So usually I don't share the links in the class. Yeah, so Nitesh is good at that. So that's all, folks, for today. And it's a bit lengthy because we would, the first part has gone. Of course, I am happy that it is because of interaction that is getting extended. Nevertheless, I hope you have enjoyed this session. We have talked about basics of the data science and the linear regression. We have run a bit fast there, but you will be able to follow that. So type E in the chat box if you have enjoyed this session, and we will see you in the next session whenever it is scheduled. Thank you all for the patience and participation. Thanks, Nitish. Thank you, Mahadev, Vanupriya, Janikraman, Deepa. Great. Good. Thanks, Funny. Sunil. Sanjay, thank you. Mayur. Yes. Thank you. Thanks, Manoj.
Hello.
Yeah.
Yeah,
Divya?
yes, sir. Thank you so much for lecturing us. Thank you.
So participants are leaving. I'll also leave.
Yes, sir. I will end the meet.
I'll share the PPT with Pratibha so that you can
Okay.
get it from there.
Yes, sir. We will submit that PPT in LMS.
Right. Thank you. Have a nice.
Thank you, sir.
Nice-
Bye bye.